All right, we've got about 8 people here now. Getting a few more. Okay. You guys don't have to leave the audio on your side unless you want to talk. You can always mute it until you want to say something. Or you could type something in the chat window. I can see that as well. All right, so who's got a question? Okay, if you want to ask a question, you can't be muted. Or you could type it in the chat window. That works too. A Gauss's law problem. Okay. Let's see. So, let's take a look at one of the cylinder ones, because I think people messed up those more than the sphere ones. So let's say that we've got an infinite cylinder that keeps going. And we've drawn a Gaussian surface around it. So let's say the radius of this circle is little r, and our Gaussian surface comes out to r. Or we could also draw a Gaussian surface inside the little r here. We can call that radius little r1. This will be little r2 out here. Okay, let's see if I can do a better job of focusing this. That didn't help. Okay, let's try this. Well, oh, okay, there we go. And is this too bright? I can, I'll just over there. Okay, so we've got our surface. This is our infinite surface here. This is our object. And let's say our object is made out of an insulator. Insulator. And would that have a surface charge density or a volume charge density? Feel free to write in the chat window. So if an insulator, are we looking at surface charge or volume? Volume charge, great. Okay, so this is going to be rho is equal to V over, oh, no, sorry, sigma, no, not sigma, wait, Q, that's it, Q over the volume. Okay, so if we've got an insulator, let's say we're starting out inside the insulator, where R1 is less than little r, which is the radius of the insulator itself. Okay, so what do we want to do? All right, the first thing we want to do is figure out which surfaces are going to have flux go through them. Which surfaces have flux? Because remember, it's only the surfaces with flux that are going to contribute to our electric field. Okay, so if we've got an infinite cylinder, where is the electric field due to that infinite cylinder pointing? Let's say it has a positive charge. Where does the electric field due to a positive charge point? You got two choices. It can point towards the object or away from the object. Positive charge. Which one is it? Away. Awesome. Okay, so our electric field is going to point away everywhere on our object. And this is a three-dimensional object, so it's going to be pointing out away here, and away here, and so on. All right, so the electric field is pointing away from our little cylinder radius r everywhere. Okay, what about the area vector? Now we want to look at the area vector of our Gaussian surface. So that's this one out here. Gaussian surface. Or it could also be this little one in here, but they're going to have the same type of area vectors. All right, the area vectors of the spherical part of the surface are going to point directly away. This is the case for the inner one and for the outer one. It's just easier to see the outer one. And what about the area vectors from the top and bottom of the Gaussian surface? Where are those going to point? If I wanted to draw it here, where should I draw it? Anybody? Okay, so the area vector always points perpendicular to the surface. This Gauss's law surface is flat in this dimension, so this is going to point straight down and straight up. And the same thing here. We're going to get an area vector pointing straight down or straight up. That's the other opposite way, obviously. All right, and these area vectors have to be parallel to the electric field in order for this to work. So if E is parallel to A, surface has flux. But if E is perpendicular to A, no flux through surface. Okay, so the only surfaces that are going to count here are going to be our circular surfaces. So the curved surface has flux, curved surface contributes to flux. Contributes to flux. Okay, so when we've determined that, the reason that we need to know that is because the flux, which we called phi, is equal to E times the area, and it is also equal to the enclosed charge divided by a constant. All right, which means once these are parallel and we are only looking at the surfaces with flux, we can say that the electric field times the area of the Gaussian surface is equal to the charge enclosed by the Gaussian surface divided by a constant. All right, are there any questions so far? Anybody stuck or missing anything? All right, a lot of people forgot to do this on the test. Now, if you don't do it for the spherical surface, it works out okay because there's only one surface there. But for a rectangular surface or anything with more than one surface, you need to figure out which ones contribute to the flux and which ones don't, or you'll end up with far more terms than you need. Okay, so we've got the electric field times the area of the Gaussian surface is equal to the enclosed charge divided by a constant. The area of the Gaussian surface, okay, this is the area of this curved surface out here that has flux going through it, this thing out here. All right, so the area of that, let's see, it's going to be equal to the circumference times the length. So let's divide, or let's call this L over here. And the circumference is 2 pi times the radius. And remember, we're inside, so we're actually looking at this one over here, which I'm going to say has the same length. This is also L. It doesn't really matter how big this is. Just call it whatever. All right, and it's got a radius on the inside of little r1. So the circumference is 2 little r1, 2 pi, no, wait, is it 2 pi r? Yeah, times pi times the length. All right, so that's the area of our tiny little Gaussian surface inside here. And then we'll do the large one outside here. Okay, that's the area of the Gaussian surface. That's the one that goes with E over here. Our Q enclosed is all the charge inside the Gaussian surface. Inside our Gaussian surface. All right, so let's figure out how much charge is in there. It's a volume, and the volume of a cylinder is pi little r, let's see, this little one, which is r1, let's see, that's going to be pi r1, it's the area of this times the length, so pi r1 squared times the length. Let's see, and this enclosed charge, we said rho is equal to Q over V, so Q is rho times the volume, so our Q enclosed is going to be the charge density times the volume, which is rho pi r1 squared L. And then we're going to rearrange E. So this is going to be Q enclosed over area of the Gaussian surface times a constant. So that's going to be rho pi r1 squared L divided by the area, which is 2 r1 pi L epsilon naught. So let's see. And R1 is going to cancel, and L is going to cancel, and a pi is going to cancel. This is leaving with both rho R1 over 2 epsilon naught. All right, so that's going to be the electric field at R1, which is smaller than the radius of the entire Gaussian surface that we drew. Okay, how are we doing so far? Does this look familiar to most people? Hopefully. Okay. Okay. I'll assume from nobody making a comment that they're good so far. All right, look, it's very important that this L cancels out here. Your Gaussian surface shouldn't just, the length of it shouldn't just cancel out on top or something. It should go away on top and on bottom. It needs to go away entirely because this really shouldn't depend on how big we drew our box. This is going to end up being the same anyway. Okay, is that what you're asking, Ellie? If that cancels in that case or just always? So L should always go away. But the size of the box probably matters as far as where it is in terms of your length of your object. So as long as we're still inside our object, which means less than little r here, we don't have to worry about subtracting any areas out here. Okay, so let's take a look at when we've got, let's see, we called it big R2, where did I write that here, is larger than little r. So case R2, which is larger than little r. All right, so once again, we're going to have E times the area of the Gaussian surface is equal to Q enclosed over epsilon naught. All right, the area of our Gaussian surface this time is the area all the way out to R2, but it's the same shape as R1, so it's just going to be 2R2 pi times L. Our Q enclosed is once again going to be rho V. So rho times the volume. But remember, we're looking at the charge enclosed, not just all of the volume enclosed. The entire volume enclosed is this whole thing here, but the charge enclosed is really only on this piece of it here. So when we say the volume, we want to mean the volume with charge in it. And that's the volume that goes out to little r, not the volume that goes all the way out to R2. So our volume is going to stop at little r. It's going to be the volume of basically this piece right here that comes out to there. All right, and that volume is going to look like the same one down here. It's going to be pi little r squared times L. And that means that our Q enclosed is going to be rho pi little r squared L. So E is going to be Q enclosed over area of the Gaussian surface times epsilon naught, which is going to be rho pi little r L squared L over our area, which is 2 pi r squared L times epsilon naught. So we're going to get pi to cancel and L to cancel, and that's it. So E, where R2 is larger than little r, the radius of the object, we're going to get rho r squared over 2 R2 epsilon naught. So that's going to be our electric field outside of there. All right, at this point, what we could do, which we didn't do last time, but what we could do is say, all right, well, I'll give you the value of these r's and rho, and epsilon's just a constant. It'll be on the exam anyway. You could find the electric field anywhere inside of here, and you could solve for the electric field anywhere outside of here. Basically, what Gauss's law is letting us do is derive an equation for that region. It's just important to remember whenever you're talking about a volume or area inside an object that goes with your Q enclosed, it only matters the extent of the one that has charge in it. It doesn't go all the way out to the furthest radius in every place. All right, are there any questions on this one before we move on to another question? Or any other examples people want to see? Okay, so how does a sphere differ? All right, so let's take a look at a sphere. So with a sphere, let's say we had a double sphere. Let's say we have a sphere in here and another sphere out here. Let's say this one is glass, which is an insulator, which means it's going to have a volume charge. And this one is copper, which is a conductor, which is going to have a surface charge. All right, we're going to call this distance R1 and this radius R2. All right, and let's find the electric field at 3 different spots. We're going to find one right in here, inside the copper only, one sitting out here between the copper and the glass, and one way out here. So we've got 3 different Gaussian surfaces. We'll call them little r1, little r2, and little r3. So we want to know E at, let's see, r1, which is smaller than little or big r1, which is the radius of the copper conductor. We want to know E at r2, and r2 is larger than r1, but smaller than big R2. And we want to know E at R3, where little r3 is greater than R2. All right, so we want to find the electric field at 3 different points here. Okay, let's see. Let's start out with the easiest one in the middle. So E1, which is going to be A times Q enclosed over epsilon naught. Okay, so A is this Gaussian surface, this one right here, that we're dealing with. So we want to look at the area of the Gaussian surface, which is the area of the sphere right inside here. The area of a sphere is 4 pi r cubed? No, 4 pi r squared. Sorry, we're looking at area. So it's going to be 4 pi little r1 squared. That's the area of our little Gaussian surface, the dotted line inside here. All right, Q enclosed is going to be equal to, let's see, either sigma times the area or rho times the volume. We're looking at a copper conductor, this one inside here. All right, for a conductor, you're going to find all the charge on the surface. So in this case, it's going to be surface times the area of the sphere. So I'm going to call this AR1 because I want to separate it from the Gaussian surface area. The one that goes out here with the E, that's our Gaussian surface because we're looking for the electric field at the Gaussian surface. The Q enclosed, on the other hand, deals with the physical object. It's the charge on the object that extends out to that radius. Okay, it goes out to there. All right, so if our Gaussian surface is out here, and our charge is only found on the surface, which is out here, how much charge is inside our little Gaussian sphere that I just drew? None, exactly. Okay, equals 0 inside copper sphere. Okay, so E1, E of R1 is simply equal to 0. All right, is everybody okay with that? Remember, if you have an insulator, if we had anything inside of here that was an insulator, we might be able to contain that. But if the entire thing on the center is, even if it's solid copper, all of the excess charge will sit on the outside. Now, there are charges inside this ball. It's just that there are equal numbers of positive and negative, so they don't create an electric field. We need to have an offset of charge, an imbalance in one direction or the other to have a field, and the offset always exists on the surface of an insulator. Okay, so let's take a look at E2. This is going to be E2, area of our Gaussian surface, is Q enclosed over epsilon naught. All right, the area of the Gaussian surface for the second one out to here is going to be 4 pi r2 squared. Let's see, and our Q enclosed. All right, out at this point, we're including the charge on this area. Now it's inside our Gaussian surface. So that's going to be sigma times the area of R1, but we're also including this piece out here, which is the volume charge on the glass insulator. So this is also going to be V times the volume. And that volume goes out to R2. It extends all the way out to big R2, but since we're only looking at what's inside our Gaussian sphere, and that only goes out to little r2, we're only going to put the volume out to that point. All right, so our area at R1 is the area of a sphere at radius R1, so that's going to be 4 pi big R1 squared. And the volume out to little r2. Okay, it's going to be the volume all the way out to here minus the volume on the inside. So that's going to be 4/3 pi little r2 cubed, which gives us the volume of this sphere, and then we're going to subtract the volume of the interior sphere to get the volume between the two. So that's going to be minus 4 pi, and this little sphere here is r1. So this is big R1 cubed, which is the same thing as saying 4/3 pi r2 cubed minus big R1 cubed. All right, so this is the volume out to R2. All right, I want to make another point, which people keep screwing up. This is a side note. R2 cubed minus R1 cubed is not the same thing as R1 minus R2 minus R1 cubed. You can't factor out the cubed here. This one just has each term cubed and then subtracted from each other. This one requires FOILing. That means you have to go all the way out the whole way each time. So this times itself again. So you're going to get all sorts of little cross terms in there. Don't simplify it that way. It has to stay like this. All right, so E2 is going to be equal to Q enclosed over a Gaussian surface times epsilon naught. So our Q enclosed is going to be sigma times the area of out to R1, which is 4 pi R1 squared. And then we're going to add to it the volume, rho times our 4/3 pi R2 cubed minus R1 cubed. And then we're going to divide it by the area of our Gaussian surface, which is 4 pi R2 squared times epsilon naught. All right, well, let's see. We can cancel a few things. We can cancel out the 4s, and we can cancel the pi's. So the best way we could leave this would be sigma R1 squared plus rho 1/3 R2 cubed minus R1 cubed divided by R2 squared epsilon naught. Okay, so this would be the electric field right in here, that this little radius sits somewhere between the insulator and the copper conductor. Now, a lot of people get confused when they start thinking about this because they think that an insulator will actually block all the electric fields from the inside, but that's not true. What it doesn't do is allow the electrons to move from the inside to the outside. That's not going to happen. But it doesn't block the electric fields. It doesn't absorb the electric fields. All of the electric fields inside will be added to everything else. They make it right through without any problems. So we've got the electric field due to the interior portion from the copper. Oh, sorry, that's this one here. And then due to the amount of the insulator that makes it out to our Gaussian surface. All the stuff outside the Gaussian surface doesn't contribute to the flux, so it doesn't contribute to our equation. All right, so our third one is all the way out here. So this is going to be, let's see, E3, a Gaussian surface, is equal to Q enclosed over epsilon naught. Now these are almost the same. A Gaussian surface in this case is going to be 4 pi R3 squared, and our Q enclosed is once again going to be sigma area R1 plus rho volume, and in this case, the volume goes all the way out to where it ends, which is at, it goes all the way out to here, because the volume is actually this big piece out here at the point, because we're all the way out here, which goes out to big R2. All right, so the only difference here is that instead of using only part of the volume, now we're using the entire volume. But we still have to subtract the interior term, so it's going to look similar. Okay, so the area of R1 is the same as before. We've enclosed the entire little sphere again. And our volume out to R2 is going to be equal to 4/3 pi. And we're going to take the outer surface, which is R2 cubed, and we're going to subtract the inner surface, which goes to R1 cubed. So last time what we did is we had a smaller bit of it. So we only went out to here and then subtracted this. But now we're going all the way out to here and subtracting this. So basically, we're going to get the entire same thing again we got below. Sigma over R1 squared plus rho 1/3. The only thing that's going to change is this term, this R2 to the third minus R1 to the third divided by R2 squared epsilon naught. Oh, sorry, this is going to be an R3 this time because we're all the way out there. From here, yep. Okay, and it's going to look almost identical. All right, and that would be the case of a sphere. And then we could have made the cylinder problem similar by basically going in and having a two-part cylinder, one part that's an insulator, one part that's a conductor, things like that, and then having to subtract the volumes on the inside there as well. But the only thing you don't have to worry about with the sphere that you have to worry about with the cylinder is the fact that the only surface, there's only one surface to a sphere, and that's the surface with flux through it. In the case of a cylinder, we've got a top surface, a bottom surface, and a side surface, and the only one with flux going through it is the side surface in this case. All right, are there any questions about that? All right, what else do people want to take a look at? A capacitor circuit where you have to find the voltage and charge on various capacitors. Sure, let's see. So let's say we've got a battery, and we've got a capacitor here, and we've got a capacitor here, and a capacitor here, and here, and here. All right, so this is our delta V. This is going to be C1, C2, C3, C4, and C5. And let's say C1, let's see, is 10 microfarads. C2 is 12 microfarads. C3 is 15 microfarads. Oops, sorry, you can't see those. C4 is 20 microfarads. C5 is 25 microfarads. All right, and did I bring my calculator? Yes, I did. Okay. All right, so we want to find the charge on all of these, and we want to find the voltage across all of these, and we want to find the energy stored in all of these. All right, so we've got three different terms we want to find here. Yes, exactly. Okay, can somebody remind me the equations for the energy with this? Does anybody have them with them? I always get them backwards. Let's write down the actual energy equations if somebody has that with them. Remember, there's three of them, but if we have one, we can just go from there because Q is equal to, oh wait, no, C is equal to Q over V, right? I think so. All right, so who's got the energy equations with them? Anybody? It should be from, what, test 2, I think? I know there's a 1/2 term in there. Let's see, what's the rest of that? There's like, I don't remember if it's CV squared or if it's just CV. Anybody find them yet? Does anybody have their sheets with them? Do I have to go look for this? Okay, Annalise is doing it. All right. Q squared over C. All right, so that would be one of them. And Q is equal to CV. So we also have 1/2 CV B squared over C, which is CV squared. So our energy equations are 1/2 Q squared over C, or 1/2 CV squared, or 1/2 QV. Okay, great. 1/2 QV. All right, so we'll stick with these. And we also need to remember this one, which I think I've gotten right, hopefully. All right. Okay, so we want to find these three quantities for all of these. All right, the first thing we need to do is simplify this circuit. We want to find an equivalent capacitance and then work backwards from there. All right, so what you want to do is take everything that you see that you know is necessarily either in series or in parallel, the simplest connection you can see, and simplify from there. The simplest connection I can see are these two right here. These are definitely in series, which means they have the same charge on them. That's true for a capacitor, for capacitors in series. All right, to add capacitors in series, the equivalent resistance of these, which we're going to call C34, is going to be 1 over C3 plus 1 over C4 to the minus 1. So this is going to be 1 over the C3 value, which I said is 15 microfarads, plus 1 over C4, which is 20 microfarads to the minus 1. Let's see. So I'm going to do 1 over 15 plus 1 over 20 to the minus 1 power gives me 8.57. So that's 8.57 microfarads. Okay, so I'm going to redraw this now using that as 1. So this is my V. I've got C1. I've got this capacitor over here. I've got an equivalent capacitor over here. And then another one over here. So I've got C1, C5, C2, and this is C34. Okay, interrupt me if you've got any questions or you think I've screwed something up. Okay. All right, so now the simplest connection I can see are these two are in parallel. And capacitors in parallel have the same voltage. Now don't try to do not try to combine things in parallel unless you're only down to one capacitor per parallel branch. Don't try to combine these in parallel up here. It's very easy to screw that up. Do the series connection first, redraw it, and then do it in parallel when you're down to one equivalent capacitor on each branch. All right, capacitors in parallel, this is going to be the equivalent 234, simply add together. So it's going to be C2 plus C34. That's going to be 12 microfarads plus 8.57 microfarads. So C234 is 20.57 microfarads. All right, let's redraw it again. So we're going to have our voltage, C1, C234, and C5. All right, so at this point, it tempted a lot of people to say that since these were on opposite sides of each other, they're in parallel. But they're only in parallel if the charge has to split before it can make it to the next one. If the same charge is going to end up on all of them, or if you imagine the same current would have to pass through all of them, they are in series. So these are actually a series connection. Same charge. Okay, so our equivalent capacitance is going to be 1 over C1 plus 1 over C23, 4 plus 1 over C5 to the minus 1. So C equivalent is going to be 1 over 10 plus 1 over 20.57 plus 1 over 25 minus 1. Okay. We've got 1 over 10 plus 1 over 20.57 plus 25 to the minus 1 power, 5.30 microfarads. Okay, so this is our C equivalent. So that is our equivalent capacitance of the entire circuit. Okay, now we want to start working backwards. Do I have any other colors of pens with me? I have a blue one and another blue one. All right, well, I'll work backwards in blue. How about that? Okay. Let's see. So we've got our equivalent capacitance, and I'm going to draw this equivalent capacitor. It's our voltage. This is our delta V, and a single capacitor Q equivalent. All right, so what we want to find is the charge on every single capacitor individually, the voltage on every single capacitor, and the energy at every single capacitor once it is finished charging. Okay, so Q equivalent is our 5.30 microfarads, and our voltage, oh, I didn't assign a voltage. Let's say our voltage is, say, 30 volts. Okay. All right, so we want to find the charge on this. We know that C is equal to Q over V. So this tells us our charge equivalent, so this would be our charge on the entire circuit, is going to be equal to the equivalent voltage, or capacitance, sorry, times the total voltage, which is going to be 5.30 times 10 to the minus 6 farads times 30 volts. And this will give us, let's see, 5.3 e to the minus 6 times 30 It's 159 microcoulombs. Okay, so there's 159 microcoulombs worth of charge moving around in this circuit. That's all we have to work with. That's the charge sitting on this capacitor. All right, let's back up a step. We could find the energy on that using any of these equations, but we're not quite there yet. What we want to do is find a certain capacitor first. Right now we're dealing with the equivalent, so we don't care about individual ones. All right, so let's back up. All right, all the charge is the same on capacitors in series. So if the equivalent charge was 159 microcoulombs, then this is 159 microcoulombs, and this is 159 microcoulombs, and this is 159 microcoulombs. All right, so we found the charge on C1 and C5 and the combination of C1 or 2, 3, 4. All right, so we're already done with two of them. Two of them we have found the charge for. We've got the charge on it. Let's find the voltage at this one. We're going to take C is equal to QV and rearrange it so V is Q over C. So the voltage on number 1 is going to be Q1 over C1. So that's going to be 159 microcoulombs divided by C1, which was 10 microfarads, which is, 1.59. 1.59 volts is sitting here on C1. C5 is going to be the same thing. Or sorry, V5 is going to be Q5 over C5, which is going to be 159 microfarads divided by C5, which was 25 microfarads. Oh, sorry. Ooh, nope. Microcoulombs. Coulombs. That's my problem, just keeping the units straight here. So we've got 159 divided by 25, 6.36 volts. 36 volts is going to be V5. So we've got a V5, we've got our V1. All right, and then we can find the energy on 1 and 5. So U1, let's see, we've got all these pieces, so we can use any of these equations. Let's just do the top one. Is going to be 0.5 times the charge, which is 159 microcoulombs squared. Remember, that's 10 to the minus 6, and then square it, divided by the capacitance, which was 10 microfarads. So the energy stored in capacitor 1 is going to be 0.5 times 1.59 e to the minus 6 to the second, divided by 10 e to the minus 6. 1.26 times 10 to the minus 7 joules. So this is the energy stored on capacitor 1. And the energy on 5 is 0.5 times 1.59 microcoulombs squared. And then that one had a charge, a charge. No, that was the charge. A C of 25 microfarads. So U5 has an energy of 5.06 times 10 to the minus 8 joules. All right, so we're done with two of these capacitors. And now we've got an equivalence here. So actually, before we back up again, remember, when we back up again, we're going to come back to we're going over here. We're going to come back to capacitors in parallel, which have the same voltage, but not the same charge. They're going to split the charge. So if we know the voltage here, then we'll know what the voltages here should be. So this has this charge. Let's find the voltage of 234. And that's going to be equal to Q234 divided by C234. So V234 will be 159 microcoulombs divided by C234, which is over here, which is 20.57 microfarads. So V234 is going to have a voltage of 159 e to the minus 6 over 20.57 e to the minus 6, 7.73 volts. Okay, If that's the voltage of the combined two in parallel, then that means C2 has 7.73 volts and C34 has 7.73 volts. All right, so we're backing up one more step. We're done with C1, we're done with C5, now we can finish up C2. C2 has, let's see, C2 is 7.73 volts, and we know C2 is 12 microfarads, so that will tell us the charge on C2. The charge on C2 is V2 times C2, which is going to be equal to 7.73 volts. Sorry, I don't know if you can see this over here. Times C2, the capacitance was 12 microfarads. So the charge on 2, let's see, 7.73 times 12 e to the minus 6. Oops. Yes? No? Okay. Which should be 9.3 times 10 to the minus 5 coulombs. So that's 0.93 microcoulombs. All right. So we've got 0.93 microcoulombs is the charge on the second one. And where was I going with that? Oh, we found out on that, so we can find U on 2, which is going to give us 1/2 the charge, 0.93 microcoulombs squared, divided by C for 2, which was 12 microfarads. So the energy stored on capacitor 2, 0.5 times 0.93 e to the minus 6 to the second divided by 12 e to the minus 6 is 3.6 times 10 to the minus 8 joules. All right, so we figured everything out for those two. Now, before we move back to the final one, where we separate C34 into C3 and C4, we need to know the charge sitting here on C34. Because when we move back and separate them into two in series, they will both have that charge sitting on them. Series has the same charge. So we want to find Q of 3 and 4. That's going to be the voltage of 3 and 4 times the capacitance of 3 and 4. So Q34 is going to equal 7.73 volts times the capacitance of C34, which we said was 8.57 microfarads. All right, so that's going to give us a charge of 7.73 times 8.7, 66.2 microcoulombs, which means C3 has 66.2 microcoulombs, and so does C4, 66.2 microcoulombs. So we're backing up the very last step. So the only thing is we don't know the voltage on each of these, and we don't know the energy in each of those. But now we know the charge, that's C3, and we know C4. Okay, so the voltage, if we rearrange ours, oh, that's equal to Q over C. So for 3 will be the Q of 3 over the capacitance of 3. So V3 is going to be 66.2 microcoulombs divided by 3, which is 15 microfarads. Okay, so that's 6.2 over 15, 4.41 volts. And that's V3. And then V4 should be 66.2 microcoulombs divided by C4, which was 20 microfarads. So V4 is going to be equal to 3.31 volts. And remember, if we add these together, we should get back about our 7.73. So 3.31 plus 4.41 is 7.72, so close enough. All right, so we're pretty much back. The charge on this one is equal to the charge on each of these. The voltage of this one is split between those two because they're in series. All right, and the last thing we have to do is find the energy in each of those. So U3 will be 1/2 times Q squared over C, so that would be 66.2 microcoulombs squared over C3, which was 15 microfarads. So the energy on the third capacitor 3, 66.2 minus 6 to the second over 15 e to the minus, minus 6. The energy on this one is 146 microjoules. And U4 will be 0.5 times 66.2 microcoulombs squared over C4, which is 20 microfarads. All right, so this one should be 110 microjoules. So this is U4. Okay, so that's how you would do this problem. So if you've got a capacitor and you wanted to find all the values of the Q's and the voltage and the energy on each of them, you start by drawing it, simplify it down, and keep drawing every time you simplify it until you have equivalent capacitance. Then you can find the charge in there, and then you start working your way backwards. You go from this one up to one more. All right, this one had a certain charge on there. Well, these are all in series, so they all have that charge. Well, now we know their capacitance and their charge. Let's find the voltage on each of them. All right, then we can step back again, and you can say the same thing. So we've got this in parallel here. We know that each of these branches has that voltage on it. So this was 7.73, so each of these was 7.73 volts. And now you have the voltage and you have the capacitance. You can find the charge on each of these. Back up again one step. This one is in series when you back up. That charge is the same on each of them. You've got the capacitance, you've got the charge, now you can find the voltage. And once you've figured out that part of the table, you can just go in and calculate the energy for the rest of it. All right, any questions on that one? Oh, for an equation sheet on the exam. Yeah, so you can bring all of your previous equation sheets, so the really long one you wrote for the last exam plus the two smaller ones you wrote for the first one, or you can rewrite those on another sheet. And I'm going to give you guys the optics sheet. I posted it on Bridges earlier today. It includes a couple of equations you don't need to know. I'll probably just put an X through those before I add it to the exam. We would have gotten to them with a couple more days, but that's okay. And so if something doesn't look familiar, probably don't really need to know it. Let's see. Yeah, so you'll have all the optics stuff on there. Yeah, so you can rewrite them if you want to. Don't bring more than 2 pages front and back, but don't put actual solved solutions to things on there. It doesn't help you as much as you think it will, and it's kind of cheating. So, especially since I already said that the final is going to be very familiar to you if you study the previous exams that we took in this class. I'm basically going to take problems from previous exams and write a different version of it and put that in. That doesn't mean just changing the answers. It means, rearranging the circuit or writing another problem that has the same kind of solution as the other one. But if it didn't show up on a previous exam and it's not optics, it won't show up in the next exam. Okay, any other questions? Okay. No, I'm going to attach that to the test itself. Also, if you need any of the brute force method equations from magnetism or from electrodynamics, I'll put those on there as well, the ones you didn't have to memorize or put on your sheet, like the ones for, say, a disk or a line of charge. And then if you need any of the moment of inertia equations, I will also put those on the exam. Okay, so optics problems, we took a look at, let's see, there was Snell's law, which included n1 sine theta 1 equals n2 sine theta 2. So that was between any two surfaces, and remember you have to draw your incident angle. So this will be theta 1, and this will be theta 2 on the way out. Remember, it's always with respect to the normal. So this would be n1 and n2. You'll definitely have to be able to use that in almost all cases. There is also the critical angle, which, remember, anything larger than the critical angle is going to suffer total internal reflection. So theta larger than theta c, total internal reflection. And the critical angle was calculated as the inverse sine of n2 over n1. So the critical angle only works if you're going from a dense medium into a less dense. It'll work for, say, water into air or diamond into water, but it won't work around the other way out. So it won't work from a less dense to a denser. You also needed to know angle of dispersion. Which was something like, let's call that angle D. That's going to be your leaving angle, your refracted angle for, say, the red light minus the blue light, or whichever one is bigger minus the other one. So the refracted angle for the blue light. So if you have a prism of some sort, you've got white light entering. If the prism has different indices of refraction for different colors, you're going to get, say, two colors bending differently here, and then coming out and bending it differently again. So the difference between these two, if this is red and this one is blue, is your angle of dispersion. What else for optics? You can have mirrors, and you can have lenses. And there might be something on polarization. Hopefully that's pretty straightforward after the questions on the homework that is due later today. But we didn't spend much time on that, so I probably won't focus on it. And I'm planning to have maybe 3 optics questions and 1 question from each of the previous exams. So, which of the previous exam questions are you confused on? Would you like to go over? What was the review test problem? Where did that come from? Okay. So our first exam was electrostatics, so electric forces and electric fields, polarization, how stuff moves around. And the second exam was electrodynamics, so Gauss's law was on the first one. That was on the first one. Electrodynamics on the second one, how stuff moves, how things react to electric fields. And then we had magnetism and waves. Don't forget waves. There was a whole bunch of stuff in there for waves. And also sound, so Doppler effect and decibels versus intensity in general. And then there was optics. Yeah. Okay, question 6 on the previous exam for optics. Okay. Does it say what year that was? Or semester? Is there a date on that one? It's number 6. Oh, it might not. Okay, let me check. One on Bridges 2015. Okay, so let's just go to Bridges. That's not what I want. Where is... Which is... Put it up here somewhere. Maybe not. Okay. I don't want that version. I want this version. Okay. So, Bridges. Put that in. Okay, I'm hoping this one I'll come up with the gradebook because that would be unprofessional. In fact, actually, I'm going to mute this just so it doesn't come up with the gradebook real quick. So I'll be right back with the screen. How do I do this? Screen sharing. Stop showing the screen for a second. Okay. It's not showing, is it? Hopefully it's not showing. All right, so I want to go to here, here, resources, previous year exams, sound and optics, question 6. Aha! Oh, okay. Yeah. All right. Is this the one you meant? Question 6 with the 2 lenses? Okay. So we didn't do a problem like this, although it's actually not too hard. Really, what you would do is you would do the problem for the first lens, and then the image it forms is treated as the object with respect to the second lens. So it's kind of like a mirror problem, where you have the 2 mirrors and they bounce back and forth treating images as objects. It works the same way for the lens. It's just a matter of keeping your math straight because you have to recenter at 0 for each lens. Yeah. So I won't give you one like that, but yeah, we could have done that with another hour. Okay. Is there another one in here you guys would like to see? Let's see, there's a couple of single lens ones, mirror, dispersion angles. What else? Oh, this is a Doppler effect problem. And wave equation, which I didn't end up putting on the exam, so you don't need to know the wave or how to solve the wave equation for this final. This one we did a couple of times, something like it. Polarization? No, probably not. There's just a couple problems on the practice, but we didn't try those. Okay, so I guess no, probably no polarization. All right, let's take a look at this one. So this is a dispersion problem. All right, and hopefully this is one of the ones where the angle I drew actually works out, but we didn't all, so I guess we'll find out. I corrected them before the exam, but then I didn't remember to correct the actual version of it that had it on there. Okay, so we've got a prism, and it has an apex angle of 26 degrees, and it is symmetric. So that means the angles down here, oh, sorry, you can't see what I'm doing. Go back to here. Okay, so the angles down here are going to be 180 minus 26 divided by 2 because there's 2 of them. So 180 degrees in a triangle minus the one we already know, and then that makes 2 of them, minus 26 divided by 2 is 77 degrees. And 77 degrees. Okay, and then let me go back to the picture again, and it's coming in at an incident angle of 31. So remember the incident angle.
Fuck this phone. Fuck this thing.
Are you trying to figure out how to get in? All right, so this one is 31 degrees. All right, and okay, let me write down the things. So this is n equals 1.76 in here. Oh, sorry, for there, and n equals 1 out here. No, not in there. 26. Okay, and symmetric. All right, at which angle will the ray of light leave the sapphire and re-enter the air? Yes, we can do that. Okay, so we'll do moment of inertia next. All right, so this one's not even a dispersion problem. This one's a little bit easier. It's assuming that the angle of refraction, or sorry, the index of refraction inside the prism, this is air and this is the prism, is going to be the same for all colors of light. So it's going to refract inside and then it's going to go out again, but it's not going to break into pieces. All right, so it's going to refract at a smaller angle in here. This is going to be some theta 2. And I'll call this theta 3 because we'll probably need that. And then it gets to this side, and I'm going to draw the normal again. And then it's going to bend away from the normal on the way out to some theta 4. Oh, let's see, theta 5 and theta 6. We'll probably need all those angles. All right, so this one's pretty easy, but this is the basic idea behind a dispersion problem. The problem with the dispersion is that you end up with 2 rays inside. The white light breaks into 2 colors, or it actually breaks into an entire rainbow, but you only care about the ends of it, the red and the blue on the ends. Then you get them on the way out and take the difference in the angle. So, theta 2, let's see. So we've got Snell's law, sine theta 1 equals n2 sine theta 2. So we've got our incident angle, and we've got n1, which is air, and we've got n2, which is prism. So theta 2 is going to be equal to n of air times the sine of the angle in the air, which is sine 1, divided by n2, and then we're going to take the inverse sine of this. So theta 2 is going to be the inverse sine of air times the sine of 31 over 1.76. So our refracted angle on the inside is going to be times 1 times the sine of 31 divided by 1.76 is going to be 17 degrees. So theta 2 right here is 17 degrees. This is the right angle, and this whole thing here is a right angle. What we need to do is we need to find theta 5 over here. The easiest way to do it is by recognizing where the right angles are. All right, so theta 3, which I drew in this corner, is going to be 90 degrees minus 17, which should be, what, 73 degrees? Yeah, so this angle is 73 degrees. So theta 6 is going to be 180 minus 26 minus 73. We're not quite, are we going to quite make it? Yes, okay, so 180 minus 26 minus 73 is 81. All right, so it's a really big angle, but it's in there somewhere. If this one is 81, then 90 minus 81 is theta 5. So that's 90 minus 81 equals 9 degrees is theta 5. So this is now our new incident angle on the way back out. So theta 4 is going to be the inverse sine of 1.76 times the sine of 9 divided by n air, which is 1. Inverse sine of the sine of 9 times 1.76 will give us 16 degrees. So 16 degrees is our angle here on the way out. So I think that's all this was asking for here is the angle on the way out. So the reason you needed the angle up here is basically to make these triangles in here. So there's a little bit of geometry when it comes to these. Okay, so any questions before we move on from this one? Nope. Okay, so we've gotten, Chris wants to do an example of moment of inertia and period from test 3. Oh, okay. If it didn't show up on a previous exam, then you don't have to study it. And basically, this kind of thing, angle of dispersion, internal refraction, all that stuff is important. Waves, there are wave problems on previous exams, but I never put a wave equation, like the ones where you have to take the second derivative and divide them. That one is not going to be on there because that is not on a previous exam. If it were there, then I might put it on there, but it's not. So waves will be on there, but not that particular type of wave problem. Okay, so we want a moment of inertia problem in period from test 3. Okay, so let's go back and find one of those. This one. So this would have been previous exams that we did, exam solutions, test 3. So let's look up one of these. Nope, take a minute. Okay, so here's one. So we've got a ball, a rod connecting it to another ball. So what were the actual things here that we need to know? Each of these balls has a radius of 12 centimeters and a mass of 1.61 kilograms. The rod had no mass, so it has no contribution to the moment of inertia, and it is 32 centimeters long. All right, and the eye of a solid sphere, which are these balls, is 2/5 mr squared. All right, and I'm going to write down the equation for the period before I forget it. It is pi I over mgd squared. Okay. All right, so this is what I was writing down. So this was one of the questions on exam 3 if you had this version of it. So basically, we're going to hang this by this point up here, I think. Is that right? Yes, we're going to hang it by the pivot point up here. And we want to know what the resulting period of the object is going to be. All right, so let's start with this equation. The mass in here is going to be the total mass of the object. Total mass of object. So that is going to be 2 times 1.61 kilograms. Those are the things with mass, so it would be 3.22 kilograms. Is that right? Probably. Okay. 2 times 1.61. Yes, 3.22 kilograms. All right, G, we're on the Earth, so this is going to be 9.81 meters per second squared. Now, a few people got to this and thought, wait, should this be positive or negative? Remember, it's only negative when we're doing kinematics. This is derived from forces. That's where we got this equation from, and in forces, we've already taken into account that this was in the negative direction, so you don't need to put a negative sign on here. All right, and the distance here, D, is the distance from the center of mass of the total object, mass of object, to the pivot point. Okay, so as far as finding the center of mass goes, there were two ways you could do it. I gave you an equation for it that was on the front page of the exam. So the center of mass of an object in the y direction, let's see, would be the y-coordinate of something times its mass plus the y-coordinate of something else times its mass divided by the sum of the masses. So if we did that this way, starting up, let's see, let's call this 0. This is the y direction, and then this is y equals 0. The y-coordinate, and it's the y-coordinate of the center of mass of each object. Center of mass here and here. So our y-coordinate would have been, this one has a center of mass here at 12 centimeters, 0.012 meters, times its mass, 1.61 kilograms, plus y2, which is here, which is going to be 12 plus 12. So this is 12, this is 24 centimeters, so 0.24 meters, plus 32 from here. So that would be 0.56 meters, plus another 12 up to the center of here is 0.68 meters. So this would be 0.68 meters times 1.61 kilograms divided by 3.22 kilograms. So the center of the mass of the whole thing should have been 0.12 times 1.61 plus 0.68 times 1.61 divided by 3.22 at 0.40 meters. Okay, but I also tried to make this pretty symmetric, so if you didn't want to do the whole thing out, the truth is both of these balls are equal. They're the same shape and the same size, so actually the center of mass is just in the middle of this thing. So it would be 12 centimeters plus 12 centimeters plus halfway up 32, which would be 16 centimeters, plus 24 centimeters, which is 40 centimeters. So it's the same thing. You could have done this either way. Some people did it out this way. Some people were like, oh, it's the middle. Yeah, that's usually the easiest way to go if I make something symmetric. So this is your D value. Oh, no, it's not. This is how far up your center of mass is from the bottom. Your D value is the distance from the pivot to the center of mass. So D is going to be the location of the pivot, which is 0.68 meters plus the last 12 here, so 0.80 meters. Oh, yeah, it's going to be. So 80 meters minus 0.40 meters, so D is going to be 0.40 meters. Yes. Okay, so that's your D value. That goes into here. So the only thing we need to know now is to find the moment of inertia of the system. The moment of inertia of the system is the moment of inertia of each individual piece of the system added together if you take into account that they are now moving around the pivot point and not their center of mass necessarily. Okay, so we've got two objects here, 1 and 2. So we're going to find the moment of inertia of 1 and add it to the moment of inertia of 2 to get the total moment of inertia. The moment of inertia of number 1 around its center is 2/5 times the mass of 1 times the radius of 1 squared. All right. This is its center of mass moment of inertia. Sorry, this one up here. That's what your moment of inertia would be if it's rotating around its center. But it's not. If we let this whole thing rotate, this whole thing, looking like this, would go up and around like that, and then come all the way back down like that. So it's going to rotate like this, not around its center. It's rotating around a point 12 centimeters away from its center. So we need to add in mv squared, where we've got the mass of 1 and it's mu d. So d1 squared. So d1 squared is this distance right here. d2 is going to be this distance, because this one has to come all the way up to here to rotate around that one. So I2 is going to be 2/5 m2 r2 squared plus m2 d2 squared. All right, but the only thing that's really different about this is the d's, because m1 equals m2 and r1 equals r2. So really, our total moment of inertia for this is going to be 2 times 2/5 mr squared plus the mass times d1 squared plus d2 squared. Okay, so that's going to be 2 times 2/5 mass of 1. This is mass of 1 at a time, so this is 1.161 kilograms times the radius of one of them, which was 12 meters, plus 1.61 kilograms, d1, which was 0.12 meters squared, plus d2, which is this distance up to here, which is the whole thing minus 12, so that was the 0.68 meters squared, like that. So your moment of inertia total should have been, let's see, 2 times 2 over 5 times 1.61 times 0.12 squared plus 1.61 times 0.12 squared plus 0.68 squared. The higher thing should have been 0.786 kilogram meters squared. All right, so now that you've got your total moment of inertia, you just plug everything into this equation. So this is going to be 2 pi times 0.786 kilogram meters squared over the total mass, which is 3.22 kilograms, times 9.81 meters per second squared, times 4.4 meters, which was the distance from the center of mass to the pivot, square rooted. Okay. Come on. Come back on. Okay. 2 times pi times the square root of 0.786 divided by 2 times 9.81 times 0.4, 1.57. 1.5 seconds is the period of motion of this. Okay, so when you're doing these problems, the important thing to write down is this equation right here, but don't forget what each of these values are. So I'd say write down this equation and then tell yourself what each of these values are. This is the total mass. That's gravity wherever you are. This is the distance from the object's center of mass to the pivot point. So find that first. And then your moment of inertia, the total one, is each of their individual ones around their center of mass plus m times the offset from the center of mass to the pivot. If it's at the center of mass, if the center of mass is at the pivot, you don't need this term. Your d is going to be 0. It's just going to go to 0. But in most cases, it's slightly offset. Here it was offset by a radius. Here it was offset by the radius plus the rod. I would recommend just going in, writing down these equations and what each of these things mean. That's probably your best bet when it comes to these. Yes, so if you need a moment of inertia equation, I will give it to you. Either the entire sheet or just the specific one you need. All right, any other questions on this? I don't know, I think you can see it all. Okay, any other questions in general? Which other ones would we like to see? Yeah, there might be. So those even those you can actually go through and solve. So if they're all identical light bulbs, give them a resistance of 1. Throw any voltage you want in there for the circuit and go through and solve for them. The brightness is the order of the current. So whichever one has the brightest or the highest current is going to have the brightest one on it. So you can always just treat those as mini resistor current or resistor circuit questions. Find the current through each of the bulbs, just assuming they all have the same resistance, whatever it is, and rank them in order of their current if you're trying to rank in order of brightness. And if you pull one out, redraw the circuit before you try to decide what's going on. Anyone that gets pulled out and not replaced by a wire is broken. No electrons will go through that circuit path anymore. Oh, you guys can see the screen, right? Can you guys see the screen? Okay, good. I remembered I muted it, but I couldn't remember if I put it back on or not. Okay. All right, any other questions? Sure. Yeah, let's go back and look at one of those. So that's not this one. That would be the previous exam. Velocity selector problem. Previous exam? Yeah, so let's go through this one. Let me write down the important parts. We've got, oops. Okay, magnetic field is pointing into the page. And the object is coming in this way. And it is lithium-7. And it is missing 2 of its 3 electrons. Missing 2 of 3 electrons. Let's see. So the velocity is 2.5 times 10 to the 6th meters per second in the I-hat direction, and the magnetic field strength is 1.4 T. And we want to find magnitude and velocity. Answer T. Oh, is it? Oh, okay. Yeah, it's possible. All right, so let's just go and rewrite this whole one. Okay, so if lithium is missing 2 of its 3 electrons, it had, originally it was neutral. So if it's missing electrons, that means it is now positive as it moves through here. All right, so one of the first questions, well, basically what you want to find here is your electric field and where it points. So we want the electric field and the direction of it. Okay, the magnetic field is pointing into the page. The magnetic force, FB, is Q V cross B. So we've got V heading off in the I direction, and we're going to cross that into B, which is going into the page, which is the minus K direction, and we have a positive isotope. So B is into the page. So our right-hand rule, we've got V heading off in that direction, that heading into the page. That tells me my magnetic force should be up, but let's check it with our triangle, IJK. This way is positive, this way is negative. So if we do I cross K, that should give us a minus J, and we've already got a minus sign in there, so it's going to be minus minus J, which is positive J. Okay, so the force of the magnetic field is pointing up, so FB points up. All right. The whole point of the velocity selector is that the magnetic field and the electric field point in opposite directions. Now, this is not always the case. It's only the case for a velocity selector. But if the magnetic field points up, the electric force is going to point down. The magnetic force points up, the electric force is going to point down. And the electric force is equal to QE. All right, we've got a positive point here, a positive ion, so that means if the force points down, then the field also points down. So the electric field points in this direction. All right, so this is part B of the problem where it says, which direction does the field point? Well, the field is pointing from the positive, away from the positive and towards the negative. So that means the top plate of this should be positive and the bottom point of this should be negative because the field points away from the top and towards the bottom. All right, so we've got our force of B, we've got our E direction, so we know E is pointed down, so E is going to be in the minus J direction. And for the velocity selector, for anything that's going to make it through, actually, let's write this out. So our Lorentz force equation tells us that the total force on the charge is going to be V cross B plus E. It's a combination of this one and this one added together. So if we say the force on the charge is equal to 0, this leaves us with plus E is equal to 0. That goes away. VB is equal to E. So V is equal to E over B for anything that makes it through our velocity selector. So that means if we rearrange this, E is equal to VB. So our electric field should be 2.5 times 10 to the 6 meters per second times B, which was 1.4 Tesla, in the minus J direction. So our electric field should have been 2.5 e to the 6th times 1.4, 3.5 times 10 to the 6th meters per second in the minus J direction. All right, so that should have been the answer to part 1. It was both this piece, which you had to get from this equation, but also the direction, which you had to do a little bit of right-hand rule stuff for. All right, and then the next part of this was asking for, oh, does it go up or down?
Why am I so fucking
Okay, so it's going to come through here, and right at this point right here, the electric field goes away. The electric field came from the top and the bottom of this, but the magnetic field's the only thing that's still there. The magnetic force still acts, but the electric force doesn't. The magnetic force is pushing up on this ion, which means as it comes in with this velocity and it experiences a force in this direction, it's going to curve up. So basically it's going to do this kind of motion while it's in here. What it's going to do is come over here and drop down here at basically 2 times whatever radius it comes out at. Okay, so this told us to compare it to an unknown element. So we've got lithium-7, which is positive, which has, it's a positive 2, that's its charge, positive 2Q. And the unknown one lands 4 times farther away. So this lands at R, this one lands at 4R. This is unknown, and it has 1 extra electron, so it has a minus 1Q charge. All right, and we know that B equals mv over QR. Sorry, let's switch back over here. All right, so B equals mv over QR. You didn't have to do a huge calculation as in plugging in all the masses and everything for this one. It's just a ratio problem. Basically, we are looking for the ratio of the masses. Yes. All right, so the mass of the lithium is going to be equal to, if we want this by itself, B QR over V. All right, both of them are going to make it through. So V of lithium equals the V of the unknown. But we'll get there in a minute. And B for lithium equals B for the unknown because they're both the same one. All right, and the mass of the unknown is going to be, oh, okay. But for the lithium, let's see, we've got plus 2 for the Q, so I'm going to put a 2 in there. And then R is just R. For the unknown, it's going to be B1 for the Q. So I'll leave it as it is because the minus goes away, its absolute value. 4 times the R over V. So if I put the mass ratio of them, I'm going to get mass of lithium over the mass of the unknown is equal to B 2Q R over V divided by BQ 4R over V. B's cancel, Q's cancel, R's cancel, V's cancel. So the mass of the lithium over the mass of the unknown is simply 2, that went the Q up there, divided by the 4 that goes with the R down here. So it is 1/2. So that means that 2 mass of the lithium equals 1 mass of the unknown. So the mass of the unknown is 2 times the mass of the lithium, which is simply 7. Its atomic number is 7. It has, 3 protons and 4, lithium is number, which, I don't remember, what did I say at the top? Lithium, 3 protons and 4 neutrons. Okay, so that gives it an atomic number of 7, because that's basically at the sign 1 to each of those. So this should have an atomic number of 14. All right, so that was the mass of the unknown. Should just be this one there. It's just comparing the ratio of the two and saying, all right, well, this one went 4 times as far, so I'll put a 4 in here. This one has 2 twice as many electrons missing or extra, so it gets a 2 up here, and then just cancel a bunch of stuff. Cool.
Hello?
Yep.
What's up?
You have any questions on this one?
Riley is at the library, I think, and
Okay.
Dave is with his girlfriend.
All right, cool. So, does anybody have any other questions?
I gotta study. Yeah, fuck. Yeah, dude, I'm just gonna be doing work all day long.
Okay.
Yeah.
So if you're gonna talk to somebody else, why don't you mute it so we don't have to hear your conversation too?
When's that exam?
It's Tuesday.
Tuesday.
So which one sucks? That's like the counting on Tuesday.
Yeah, I have
All right. Anybody else have a question?
on Tuesday.
Ooh, fuck that.
Yeah, it sucks.
I feel your pain.
Oh, that sucks. All right.
I'm gonna get back to your.
Sounds good. I'll talk to you later.
All right. Does
Hello?
anybody else have a question? Who am I muting? All right. I'm gonna mute Rowan just in case. All right. Okay. All right, Ellie. What other question do you have? The electric field. Okay, so let's go back to exam 1. Let's see. Okay. Do you want to go over any of the questions from page 1 of exam 1? 1, 2, or 3? Let's see. How about page? Well, we just did one of those. This was potential energy, one of the hoop ones. Oh, okay. So one of these. All right. So for these kinds of questions, you need the brute force equations. So this would be on a sheet that I give you if you need any of these equations. If you don't have the sheet, you don't need the equation. Yes. So I will give you the equations. The thing to remember for these, let's see. So this one has a ring down here with a radius of big R. And then there's a little disk up here with a radius of little r. And their centers go right through each other up like that. X and Y and Z. Okay, so this is a ring, and the electric field due to a ring is K Q Y over R squared plus Y squared to the 3/2. And then E due to a disk is 2 pi k sigma 1 minus y over r squared plus y squared 1/2. These are both in the j directions here. And, whoops, sorry. K, the value for k. I should have put that on here. All right, I have to remember to put those on there. It's 8.99 times 10 to the 9th Newton meters squared per c squared. Okay. So yes, I will give you these equations. All right. Oh, I forgot what I was looking for. What are we looking for? We are looking for the force on the charge located at P. And this charge here is 17 microcoulombs. Oh, what else do we have? The ring is carrying Q1 equals minus 46 microcoulombs. And the disk is Q2 of 85 microcoulombs. And the total height here is 44 centimeters. And that distance is what? P is at 24 centimeters. Oops. Okay. All right. So the distance between the ring and the disk is 44 centimeters. The distance between the ring and the charge that we want to find the force on is this distance. So the force on the charge located at P. And remember, the force is simply equal to Q times the electric field. So it's going to be this charge Q, that's this one here, times the electric field at that location. So what we really want to find is the electric field at P. So that's going to be this one. So the force on P is the Q times the electric field on P. That's a question mark. All right. So the electric field at P is basically this equation plus however far away you are from these things, which I believe is the y. So this is your distance that you're going in each case. That one and that one. Okay, so the electric field due to the ring at P. And this points, let's see, it's going to point away from the ring. So E field, let's see, this is a positive Q value, so it's going to point this way up here, and down here it's going to point that way. So this, at point P, it's pointing away from, oh, sorry, the ring. The ring's the other one. Where's my eraser? Oh, no, this is okay. That's for the disk, though. So that's for the disk. And then this one for the ring, the electric field is pointing towards it because it's negative. So if you're beneath it, it would point up. If you're below or above it, it's going to point down towards it. So for the ring, this is going to point down towards it. So this is going to be in the minus J direction. Put that out front. Okay, and then it's going to be K, Q, 1 was the ring, times the distance between P and the center of the ring. That's our 24 centimeters, 0.24 centimeters, or sorry, meters. Actually, you know what? Let me just put the numbers in here. So it's going to be K, which is 8.99 times 10 to the 9th Newton meters squared per centimeters, or Coulomb squared, times Q, which is the Q of the ring itself, absolute value. So 46 times 10 to the minus 6 coulombs, times Y, which is the distance between the ring, and P, which is 0.24 meters, divided by the radius of the ring, which was, did I write that down? No, okay. The radius of the ring, big R is 35 centimeters, 0.35 meters squared, plus y squared, 0.24 meters squared. And we're going to take this whole thing to the 3/2 power. Okay. So 8.99 e to the 9th times 46 e to the minus 6 times 0.24 divided by 0.35 to the second plus 0.24 to the second to the 3/2 power gives me 1.30 times 10 to the 6th newtons per coulomb in the minus J direction. All right, so that's the E field due to the ring. Now we want to find it due to the disk, and then we'll just add them together. Disk at the location P. All right, at P, the E field due to the disk is pointing away from the positively charged disk. It is also in the minus J direction. Okay, and then that equals times the equation for the disk, which is up here. All right, before we do this, let's figure out that sigma value. Now remember, sigma is charge over area, and the radius of the disk is 27 centimeters. So this is going to be the total charge on the disk, which we said was 85 times 10 to the minus 6 coulombs, divided by the area of the disk, which is pi r squared, 0.27 meters squared. So our sigma value, 85 e to the minus 6 divided by, in parentheses, oops, pi times 0.27 to the square, 3.71 times 10 to the minus 4, and that would be coulombs per meter squared. All right, so now we can put that into the one above it. These equations you should have written down, the sigma and the rho and the linear charge density lambda. All right, so that's going to give us 2 pi, 8.99 times 10 to the 9th. We're doing this equation, Newton meters squared per Coulomb squared. Sigma 3.71 times 10 to the minus 4 coulombs per meter squared times 1 minus y. Okay, y is going to be the distance between the disk and where you're measuring the field. So it's going to be 44 centimeters minus 24 centimeters. This is going to be 20 centimeters divided by its radius, 0.27 meters squared, plus the distance, 0.2 meters squared, square rooted. Whoops, okay. Yes, you can do that, Annalise. Okay, all right, so this is going to be 2 times pi times 8.99 e to the 9th times 3.71 e to the minus 4 times 1 minus 0.2 over the square root of 0.27 to the squared plus 0.2 to this, oh wait, no, yes, to the squared, and parenthesis a few times, and I get this E field for the disk is 8.48 times 10 to the 6th newtons per coulomb, again in the minus j direction. So my, I should move this over here. My total E field is going to be E for the ring plus E for the disk. So E is going to be 1.30 times 10 to the 6th newtons per coulomb plus 8.48 times 10 to the 6th newtons per coulomb. So it's going to be 1.3 e to the 6 plus 8.48 e to the 6. It's going to be negative 9.78 times 10 to the 6 newtons per coulomb in the j hat direction. And the negative came because I'm moving the negative over there for the j. That's the E field. Now we want is the force, which is Q times E. And the Q at the location P is 17 microcoulombs. So 17 times 10 to the minus 6 coulombs times the E field, which is minus 7.98 times 10 to the 6 newtons per coulomb. The force is going to be 17 e to the minus 6 times 78 e to the 6, negative 166.3 newtons in the j direction. So this is the minus j direction. Okay, so that's the force I get on here. Let's see, is that what I got last time? Hopefully. Oh, nice, perfect. I even remember my units. Don't forget your units. Okay. Any questions about this one? So all to remember here was the force is equal to Q times E. That should be a very prominent equation on your equation sheet somewhere. And then the E field at that point is simply the E field calculated at that distance away from every object that is contributing an E field. The only thing to remember there is they might not be pointing in the same direction. So start out by drawing the E field. If it's a positive object, it's pointing away. If it's a negative object, it's pointing towards it. Okay, any other questions? Okay, we're losing some people. I'm going to take that as a good sign. Anybody else have a question they want to go over? This is 66. Okay, cool. All right, well, I'm going to hang out for the next 20 minutes just to make sure nobody else signs in and has a question. If anybody else has one, feel free to ask it. So if anybody else has a question they want me to answer, just go ahead and ask it in the chat window below or turn on your microphone. You can also ask questions from the homework that's due tonight, since any of those might be on the exam too. Let's see. Are all the optics practice tests a good information of problems for the final? So let's go back and take a look at these. So the practice exam for optics. Let's see. These are RC circuit problems. Wait, this one doesn't have optics in it. What am I looking for? Oh, that was like practice exam number 2 or something. Previous year exams. Sound and optics. That's a good string problem. We won't have this one. And that could happen. Let's see. This one, very likely something like that. Maybe even counting dispersion will occur. So that's a good one to look at. Something like this, yes, this is a good problem to look at. This one, no, that one's a little bit too complicated. We didn't get to that. Let's see, any others on here? There's that one, and then there's also, oh, this is the optics sheet. Let's see, did I give you guys any one of this one's up since November? I guess those are the only optics problems. Optics sheet, except for the homework. And anything on the homework could show up on there too. Probably not polarization though, because we didn't really spend much time on that. All right, so on here, we did flat mirrors, we did concave and convex mirrors. This is the same equation I gave you guys over here. It's just that 2 over r is the same thing as 1 over f, or 2 over c is the same thing as 1 over f. So these are actually the same equation. These are your rule for mirrors, and these are your rules for lenses. This is your r over 2. That's the same thing we have over here. These are the sign conventions for refraction. The ones you want are the sign conventions for mirrors and for thin lenses. We did not do this stuff over here where we're combining several mirrors or lenses together. So we're not going to put that up there. This is useful. This one we did not do, where there's different radii of curvature on each side, so you can ignore this one. I'll probably cross these out when I put it on the sheet, just the ones you don't need to know, so it's not confusing you. This one you need to know. This is when you have multiple mirrors again. We won't be doing that one. And then this is true down here for everything. Yep, so probably the homework for the optics is the best way to go. I do have the solutions for the first topic homework scanned in, but I can't seem to find them. So I'm going to put up solutions to both optics homeworks tomorrow early morning. So if you have any questions on those, I will be around a little bit. I'll probably be back by 4:30. I have a ton of meetings tomorrow, but you might be able to catch me before 10, noon to 1 if I don't have a meeting then, and 4:30 on in the classroom. But of course, our exam starts at 5. But if you're not taking it tomorrow, then you've got plenty of time to ask me optics questions. Yeah. All right. Okay, so I'll hang out a few more minutes if anybody comes up with one.